In quantum mechanics, the Hamiltonian is the operator corresponding to the total energy of the system. It is usually denoted by H, also E or a currency. Its spectrum is the set of possible outcomes when one measures the total energy of a system. Because of its close relation to the time evolution of a system, it is of fundamental importance in most formulations of quantum theory. Introduction. The Hamiltonian is the sum of the kinetic energies of all the particles, plus the potential energy of the particles associated with the system. For different situations or number of particles, the Hamiltonian is different since it includes the sum of kinetic energies of the particles, and the potential energy function corresponding to the situation. The Schrödinger Hamiltonian, one particle. By analogy with classical mechanics, the Hamiltonian is commonly expressed as the sum of operators corresponding to the kinetic and potential energies of a system in the form where is the potential energy operator and is the kinetic energy operator, in which m is the mass of the particle, the dot denotes the dot product of vectors, and is the momentum operator, wherein a is the gradient operator. The dot product of a with itself is the Laplacian A2. In 3 dimensions using Cartesian coordinates, the Laplace operator is. Although this is not the technical definition of the Hamiltonian in classical mechanics, it is the form it most commonly takes. Combining these together yields the familiar form used in the Schrödinger equation, which allows one to apply the Hamiltonian to systems described by a wave function I, R, T. This is the approach commonly taken in introductory treatments of quantum mechanics, using the formalism of Schrödinger's wave mechanics. Many particles, the formalism can be extended to n particles. Where is the potential energy function, now a function of the spatial configuration of the system and time, and is the kinetic energy operator of particle n, and an is the gradient for particle n. an2 is the Laplacian for particle using the coordinates. Combining these yields the Schrödinger Hamiltonian for the n-particle case. However, complications can arise in the many-body problem. Since the potential energy depends on the spatial arrangement of the particles, the kinetic energy will also depend on the spatial configuration to conserve energy. The motion due to any one particle will vary due to the motion of all the other particles in the system. For this reason, cross-terms for kinetic energy may appear in the Hamiltonian. A mix of the gradients for 2 particles, where m denotes the mass of the collection of particles resulting in this extra kinetic energy. Terms of this form are known as mass polarization terms, and appear in the Hamiltonian of many electron atoms. For n interacting particles, that is particles which interact mutually and constitute a many-body situation, the potential energy function V is not simply a sum of the separate potentials. The potential energy function can only be written as above, a function of all the spatial positions of each particle. For non-interacting particles, that is particles which do not interact mutually and move independently, the potential of the system is the sum of the separate potential energy for each particle, that is. The general form of the Hamiltonian in this case is where the sum is taken over all particles and their corresponding potentials. The result is that the Hamiltonian of the system is the sum of the separate Hamiltonians for each particle. This is an idealized situation. In practice, the particles are usually always influenced by some potential, and there are many body interactions. One illustrative example of a two-body interaction where this form would not apply is for electrostatic potentials due to charged particles, because they certainly do interact with each other by the Coulomb interaction, shown below. Schrödinger equation. The Hamiltonian generates the time evolution of quantum states. If is the state of the system at time t, then this equation is the Schrödinger equation. It takes the same form as the Hamilton-Jacobi equation, which is one of the reasons H is also called the Hamiltonian. Given the state at some initial time, we can solve it to obtain the state at any subsequent time. In particular, if H is independent of time, then the exponential operator on the right-hand side of the Schrödinger equation is usually defined by the corresponding power series in H. One might notice that taking polynomials or power series of unbounded operators that are not defined everywhere may not make mathematical sense. Rigorously, to take functions of unbounded operators, a functional calculus is required. In the case of the exponential function, the continuous, or just the holomorphic functional calculus suffices. We note again, however, that for common calculations the physicist's formulation is quite sufficient. By the homomorphism property of the functional calculus, the operator is a unitary operator. It is the time evolution operator, or propagator, of a closed quantum system. If the Hamiltonian is time-independent, U, T, form a one-parameter unitary group. This gives rise to the physical principle of detailed balance. Dirac formalism, however, in the more general formalism of Dirac, the Hamiltonian is typically implemented as an operator on a Hilbert space in the following way: the eigenkets of H, denoted, provide an orthonormal basis for the Hilbert space. The spectrum of allowed energy levels of the system is given by the set of eigenvalues, denoted A, solving the equation. Since H is a Hermitian operator, the energy is always a real number. From a mathematically rigorous point of view, care must be taken with the above assumptions. Operators on infinite-dimensional Hilbert spaces need not have eigenvalues. However, all routine quantum mechanical calculations can be done using the physical formulation. Expressions for the Hamiltonian. Following are expressions for the Hamiltonian in a number of situations. Typical ways to classify the expressions are the number of particles, number of dimensions, and the nature of the potential energy function, importantly space and time dependence. Masses are denoted by m, and charges by q. General forms for one particle: free particle, the particle is not bound by any potential energy, so the potential is zero, and this Hamiltonian is the simplest. For one dimension and in three dimensions. Constant potential. Well, for a particle in a region of constant potential V equals VO, in one dimension, the Hamiltonian is in three dimensions. This applies to the elementary particle in a box problem, and step potentials. Simple harmonic oscillator. For a simple harmonic oscillator in one dimension, the potential varies with position, according to where the angular frequency, effective spring constant K, and mass m of the oscillator satisfy. So the Hamiltonian is. For three dimensions, this becomes where the three-dimensional position vector or using Cartesian coordinates is, its magnitude is. Writing the Hamiltonian out in full shows it is simply the sum of the one-dimensional Hamiltonians in each direction. Rigid rotor. For a rigid rotor that is system of particles which can rotate freely about any axis, not bound in any potential, Hamiltonian is where x, I, and is are the moment of inertia components, and are the total angular momentum operators, about the x, y, and z axes respectively. Electrostatic or Coulomb potential. The Coulomb potential energy for two-point charges Q1 and Q2, in three dimensions, is. However, this is only the potential for one point charge due to another. If there are many charged particles, each charge has a potential energy due to every other point charge. For n charges, the potential energy of charge Qj due to all other charges is where I, Re, is the electrostatic potential of charge Qj at Re. The total potential of the system is then the sum over J. So the Hamiltonian is electric dipole in an electric field. For an electric dipole moment deconstituting charges of magnitude Q, in a uniform, electrostatic field E, positioned in one place, the potential is. The dipole moment itself is the operator. Since the particle is stationary, there is no translational kinetic energy of the dipole, so the Hamiltonian of the dipole is just the potential energy. Magnetic dipole in a magnetic field. For a magnetic dipole moment I1/4 in a uniform, magnetostatic field B, positioned in one place, the potential is. Since the particle is stationary, there is no translational kinetic energy of the dipole, so the Hamiltonian of the dipole is just the potential energy. For a spin of 1/2 particle, The corresponding spin magnetic moment is, where Gs is the spin gyromagnetic ratio, E is the electron charge, S is the spin operator vector, whose components are the Pauli matrices, hence. Charged particle in an electromagnetic field, for a charged particle Q in an electromagnetic field, described by the scalar potential I and vector potential A, there are two parts to the Hamiltonian to substitute for. The momentum operator must be replaced by the kinetic momentum operator, which includes a contribution from the A field. Where is the canonical momentum operator given as the usual momentum operator? So the corresponding kinetic energy operator is, and the potential energy, which is due to the I field. Casting all of these into the Hamiltonian gives energy eigenkit degeneracy, symmetry, and conservation laws. In many systems, two or more energy eigenstates have the same energy. A simple example of this is a free particle, whose energy eigenstates have wave functions that are propagating plane waves. The energy of each of these plane waves is inversely proportional to the square of its wavelength. A wave propagating in the x direction is a different state from one propagating in the y direction, but if they have the same wavelength, then their energies will be the same. When this happens, the states are said to be degenerate. It turns out that degeneracy occurs whenever a non-trivial unitary operator U commutes with the Hamiltonian. To see this, suppose that is an energy eigenkit. Then is an energy eigenkit with the same eigenvalue, since U is non-trivial, at least one pair of and must represent distinct states. Therefore, H has at least one pair of degenerate energy eigenkits. In the case of the free particle, the unitary operator which produces the symmetry is the rotation operator, which rotates the wave functions by some angle while otherwise preserving their shape. The existence of a symmetry operator implies the existence of a conserved observable. Let G be the Hermitian generator of U. It is straightforward to show that if U commutes with H, then so does G. Therefore, in obtaining this result, we have used the Schrödinger equation, as well as its dual. Thus, the expected value of the observable G is conserved for any state of the system. In the case of the free particle, the conserved quantity is the angular momentum. Hamilton's equations in classical Hamiltonian mechanics have a direct analogy in quantum mechanics. Suppose we have a set of basis states, which need not necessarily be eigenstates of the energy. For simplicity, we assume that they are discrete, and that they are orthonormal, that is. Note that these basis states are assumed to be independent of time. We will assume that the Hamiltonian is also independent of time. The instantaneous state of the system at time t can be expanded in terms of these basis states, where the coefficients n, t, are complex variables. We can treat them as coordinates which specify the state of the system, like the position and momentum coordinates which specify a classical system. Like classical coordinates, they are generally not constant in time, and their time dependence gives rise to the time dependence of the system as a whole. The expectation value of the Hamiltonian of this state, which is also the mean energy, is where the last step was obtained by expanding in terms of the basis states. Each of the n, t, s actually corresponds to two independent degrees of freedom, since the variable has a real part and an imaginary part. We now perform the following trick: instead of using the real and imaginary parts as the independent variables, we use n, t, and its complex conjugate n, t. With this choice of independent variables, we can calculate the partial derivative. By applying Schrödinger's equation and using the orthonormality of the basis states, this further reduces to. Similarly, one can show that if we define conjugate momentum variables I(n) by, then the above equations become, which is precisely the form of Hamilton's equations, with the s as the generalized coordinates, the s as the conjugate momenta, and taking the place of the classical Hamiltonian. See also, Hamiltonian mechanics, operator, bracket notation, quantum state, linear algebra, conservation of energy, potential theory, many-body problem, electrostatics, electric field, magnetic field. References